I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. I want to show you an example problem using Google Sheets to solve a fairly common problem in thermodynamics, which addresses an issue that's common to most of us, which is global warming and the idea of sequestering CO2. So in looking at this, being inspired by geology, the way the Earth has decided, has sequestered most of the CO2 it's had in its atmosphere over its lifetime is by sequestering it into minerals as carbonates. So taking oxides and then adding CO2 to form carbonates. And then we often do the opposite, which is looking at the decomposition of those. And as you can imagine, if you want to sequester it, one of the things you might want to do is to pick the oxide that, that makes it the hardest, to decompose the carbonate back into CO2 and its oxide. And so this is common in the alkaline and the alkaline earths. That all of them, they're oxides. You can add CO2 to form the carbonate, and then the decomposition is the carbonate to form the oxide and the following CO2. It's often used where these are often acid catalyzed decompositions so that you can take these carbonates, add it into an acidic solution, and get CO2 bubbling off with the metal oxide. And so that's used in a fair number of industrial processes as well. But what we want to look at is the thermodynamics. And what I want to show you today is something where instead of just calculating it by hand, which is fairly easy to do, I want to show you how potentially using something like a spreadsheet or a computational can often help visualize this and make a repetitive set of calculations easier. So what I've asked in this problem was to compare the alkaline earths from beryllium down to barium and just ask of those, group 2, which one, in a sense stores the CO2 best, meaning which one will decompose at the highest temperature so that it'll hold on to the CO2 and not let it out into the atmosphere. Is it, and we all know that in the groups of the periodic table, we generally get trends, so we're kind of expecting a trend. And just that, are we going to end up better on the lighter side with beryllium or on the heavier side, with barium? And we could make some basic chemistry arguments of why, but let's really just calculate this from a thermodynamic perspective. And so we can look up for the carbonate, the oxide, and of course CO2, we can find heat capacities, formation enthalpies, entropies for formation, and therefore we can calculate the Gibbs free energy of formation of all of these. And through that then, we're looking at the same reaction, so we can for this reaction, we can take the formation enthalpies or entropies of the products minus the reactants to get the overall change in energy for this system. And we can do that, at a bunch of different temperatures. That's a lot of repetitive calculations, right? And so instead of that, we can put it into a spreadsheet, use formulas within the spreadsheet which are taking into account the various enthalpies and entropies of the system, and then we're able to just so we can use it for all the different metal oxides and get the overall reactions out of it, and now we can just plot it and see. So this makes a much more visual way, and you can see where. So we're plotting the free energy, and where it crosses 0 and goes negative is where it'll be spontaneous, from the carbonate decomposing into CO2 and the oxide. So you can see that, beryllium is at low, temperature, and then it goes up as you go to Magnesium, calcium, and finally barium decomposes at the highest temperature. So this gives us a visual way to see this of where that reaction becomes spontaneous. And now allows us to, very easily, change these to say the alkalis by just changing these and recalculating everything on the fly. So I hope this helps show how you can use something like a spreadsheet program to take into account doing a series of calculations, very easily, and then being able to graphically represent them. Thank you.